Welcome to Lecture 25D, entitled Superposition of Vector Fields. The material for this lecture comes from Section 2.4 of Reading Assignment 5, the short version. Reading Assignment 0, Section 5, and again this is for only reference purposes. And also you can look at the archived lecture video 25C for reference purposes. The objectives here are to apply the principle of superposition to compute a vector field given a number of sub-problems positioned at different locations and potentially formulated in different coordinate systems. The concepts and definitions that will be applied here are the principle of superposition for vector fields, coordinate and variable transformations, moving from one reference frame into another. There's also the translational transformation with respect to a measurement point. So for example, you could have a cylinder which basically is displaced with reference to the axis of symmetry, which would typically be along one of the principal axes, and also then applying the superposition principle. The next slide is just a summary of the contents of this lecture. All right, so what is the superposition procedure? All right, for this particular teaching model, we're going to assume that the field for the individual objects is known, but in actual fact, we'll be able to calculate these. And this is what we'll be doing later on in Reading Assignment 5. And this typically is a situation that exists when we basically know we have conditions of symmetry, in which case we'll be able to use the divergence theorem and Stokes theorem to extract information about the actual fields themselves. And we're going to just look at two specific case studies. One would be involving an infinitely long cylinder and an infinite plane spaced apart. If we were to solve this problem as is, it'd be too difficult. In contrast, if we can solve the cylinder problem with respect to its axis of symmetry as one problem, and the planar problem with respect to its plane of symmetry as another problem, in other words, two separate problems, then this is a much simpler calculation. And then we can use superposition to put the two pieces together. This case study 2 is more or less the same problem as above, but with different field properties for the cylinder and a different reference or measurement point. In other words, where do we want to actually calculate the total field? All right, so the generic problem statement is as follows. Compute the field for each subproblem and then compute the total vector field. That's more or less how the problems will be set up. The procedural steps are as follows. There are 4 in total. First of all, you solve the field for each subproblem in a coordinate system that exploits the symmetry of the problem. In this particular set of examples that will be given, 2 in total, the fields are already given, and so we can bypass this step. Later on in Reading Assignment 5, you actually have to first do step 1, that is, determine what the field looks like. Second step is convert the field solution for a particular subproblem in a particular coordinate system into Cartesian coordinates. Thirdly is to translate the plane of symmetry or axis of symmetry or point of symmetry, and these symmetries basically relate to different types of objects. So if we're talking about an infinite plane, it's planar. If it's a cylinder, then it's an axis symmetry. If it's a sphere, then we talk about a point of symmetry. What we need to do is translate everything back to its original location in terms of where the calculations are to be taking place. And the last step is to sum the resulting vector fields at the desired reference point, the actual physical point at which you want to calculate the total field. All right, so a couple things here just to review. Unit vectors and variable transformations. Just a reminder that the labeling of unit vector directions in a particular coordinate system must satisfy right-handed coordinate system. The table below just illustrates different combinations which are possible. In other words, in the lectures so far, we've always assumed that Z is pointing upwards and that R and theta are on the XY plane or parallel to the XY plane. Doesn't have to be so. You can basically choose other axis to basically set up a cylindrical coordinate system, but you just have to make sure that you basically do the transformation correctly in order to achieve a right-handed coordinate system. And so this table basically illustrates how that's to be done. You can do this for other coordinate systems, so it might be useful for you to try and generate such a table for spherical coordinates. Anyways, in this course, the only transformations that we'll be using are the ones shown below. That is, we've got theta hat In this case, I'm assuming that we're dealing with conventional r and theta being in the xy plane. So this is what theta hat would look like. And this is what r hat would look like if we're dealing with cylindrical coordinates. And if we're dealing with spherical coordinates, then we're dealing typically with r hat vector. In fact, in that case, we're looking at a vector, a unit vector that looks like this. So that's the x hat component, y hat component, and z hat component. All right, so let's do case 1, an example. The problem statement shown here is a slab of infinite extent has its top surface located at z equals minus a and a bottom at z equals minus a minus d. A and d are positive coefficients. In addition to the slab, we have a cylinder of infinite length, and the cylinder of radius r has an axis symmetry that passes through the point 0, 0, b and is parallel to the x-axis. B is a constant, b is greater than r. The field F1 due to the cylinder with respect to the cylinder's axis of symmetry passing through the point 0, 0, b is this set of expressions that you see here. So you'll see, for instance, that if you're outside the cylinder, then the field takes on a certain description. If you're basically inside, it takes on a different description. We'll be basically proving these entities later on in the course. For the field F2 due to the slab with respect to the plane of symmetry, and we're placing at the center of the slab, which is at this location, we end up basically with a field distribution that looks like this. So we have above the slab, below the slab, and any point between the top and bottom of the slab. Again, this will be determined later on in the course. And so the two questions are, first of all, sketch a YZ trace for the problem and label all important features, including the measurement point, also called reference point, critical dimensions, the variables and field directions for each field. Once we've done that, the next step is to go through the procedure, which we basically outlined to compute the total F, which is going to be the sum of the two fields, but both of these fields will be in Cartesian coordinates, but translated to their appropriate point. And the measurement point for this example is actually at the origin. So first step is figure, and so let's see what that looks like. So here, for instance, is the reference point. Here's the cylinder. Here's radius r. This is the field direction according to theta hat. 0, 0, b is the point through which it passes. So this basically extends outwards from the page in an infinite direction, in and out. Here's the slab. This is the location. Here's the plane of symmetry, which is located at the halfway point. And in this case, the field directions are shown to be in this direction above, certain direction below. There's also field distribution inside, but again, it's too cluttered, but the expressions basically would indicate what that field would look like. All right, so the second part of the problem was to compute the total field, that is the contribution of the cylinder and that of the slab at the position 0, 0. And so first step would be to transform the equations for the field for this cylindrical object from cylindrical coordinates to Cartesian coordinates. And because the field lies on the YZ plane, it means that the theta hat basically has to be set up in such a way that it satisfies the right-hand convention. And that's the case if we basically show that theta hat basically takes on this vectorial form, which is this is in Cartesian coordinates, but theta hat in terms of Cartesian coordinates on the YZ plane would have this form. All right, so the procedure would be, the first stop would be to solve the field for the subproblems in a convenient coordinate system. However, in this problem, essentially we've already given you the field, so we can skip this step. Instead, we move on to step 2, which is to express the field F1, which is in cylindrical coordinates in terms of Cartesian variables and unit vectors. And so it's just taking this information and transforming it over here. We can see that the theta hat vector has this form in Cartesian coordinates, and of course in the zy plane, r, which is the radius, will take on the value square root of z squared plus y squared. And so all we do is to take the previous expression that we'd had for F1 in terms of the field inside the cylinder and the field outside the cylinder. This is outside the cylinder, that's inside the cylinder. So wherever we saw r, it's basically now replaced by the square root of z squared plus y squared, and theta hat basically just gets replaced by the expression that we see here. And so that's more or less what we've done here. This is just some further simplification. If we multiply through by square root of z squared plus y squared and bring this out as a common cofactor, then this is just z squared plus y squared times this vector. And similarly, in this case, you get cancellation of the numerator and denominator terms, and so we're just left with this as being the final expression, and this would be for the situation where we're computing the field inside the cylinder, that is x squared plus z squared plus y squared is less than or equal to r squared. And this is for the case where we're outside the cylinder, and the case is inside the cylinder. So the reference point for these field calculations is taken to be exactly at the axis of symmetry. All right, so step 3 is to rewrite both F1 and F12 with respect to plane of symmetry or axis of symmetry or point of symmetry, translate it back to its original location. So the point 0, 0, b passes through the axis of symmetry for F1, and the point 0, 0 minus a minus d over 2, through which the plane of symmetry for F2 passes, are different from the origin. Hence, we will simply cannot add the Cartesian expressions for F1 and F2 because the reference points are different. And so the solution is as follows. Suppose the point through which the axis of symmetry, plane of symmetry, point of symmetry passes for a specific vector field is some point x naught, y naught, z naught. So that's basically where the calculations were given to you in the first place. Now consider a point x1, y1, z1 where we want to find the total field. That is what we call the reference point or measurement point. The coordinates of this point with respect to the axis of symmetry, plane of symmetry, point of symmetry, which basically would have been designated by these coordinates, would be essentially the difference between the two. So this would be x1 minus x naught, y1 minus y naught, z1 minus z naught. So these are the transformed variables that we'll be using to basically translate everything back to its original location. All right, so for the cylinder, basically I've done this expression. And for the slab, I've done the expression here. And so you can see what we need to compute is x1 minus x naught. The x naught, y naught, z is given. x1, y1, z1 is given. So we make basically this calculation. And then this becomes a new coordinate system, new coordinates that we're working with. We take the original values for F1 in Cartesian coordinates. Z basically gets replaced by Z1 minus Z naught and Y by Y minus Y naught. Everywhere you see basically just everything being replaced. And if we go through the calculations, we find that this is the total field, which is the field now at the observation point due to the cylinder. Similar with the slab, we go through a similar calculation. In this case, basically, it turns out that we end up with an expression where the field basically is 1. So this is basically outside. A plus d is greater than d over 2, so it's above the slab. So this is the appropriate calculation that we should be using. This goes back to the original problem statement. All right, finally, now that we have both of these fields, everything in its right location, we can add them together. And so this now becomes the total field as observed at the observation point, which was at the origin. Okay, so let's do number case 2. This one actually is discussed in archive tutorial video 9. If you want to look at it, that's fine. In this case, we assume a geometrical layout for this infinite cylinder and slab, as in the previous example, with the following exceptions. The direction, the magnitude of the vector fields F1 and F2 are different, and the location of the reference point, we're called observation point, has been changed to basically be midway between the top and bottom face of the slab. So we're going to redo the calculations, assuming the following description of the vector field F1 and the vector field F2. Notice here it's a radial field, and in this case, basically, it's a field that is pointing perpendicular to the slab, both on the top and on the bottom. The points through which the axis of symmetry for F1 and plane of symmetry for F2 pass are the same as in the previous question. And so the two questions are shown here. First, sketch a YZ trace and label all the important features, including the measurement point, critical dimensions, variables, and field direction for each field. And then the second step is to compute the total field, but now we're computing it at a different measurement point, which was the midway point through the slab, located at Z component minus A minus D over 2. All right, so this is the figure that now that we're considering. Notice now that the field is radial here. And notice also here that the field base is perpendicular to the upper surface and perpendicular to the lower surface, the only difference being the directions have changed. And then, of course, there'll be a field distribution inside the slab, but it's difficult to show here. But if you look at the original problem statement, you can see what the expressions would look like inside the slab. The reference point for this example is right here, midway point between the upper and lower face of the slab. So now the calculation is going to take place here, but with two different field descriptions. All right, so the second part of the question was to compute the total field at the position 0, 0, minus a minus d over 2, which was the halfway, the plane of symmetry for the slab. And in this case, for the cylinder, the field is radial, and so the appropriate choice for transforming from one unit vector to another is the expression shown here. In this case, since we're on the YZ plane, the unit vector takes on this form shown here. So first part of the problem is to solve the subproblem in a convenient coordinate system. We've given all the information, so in fact we can skip step 1. For step 2, basically, we're taking the appropriate expressions for F1, and that would be exterior. Turns out that the observation point is exterior, so we make the substitutions in here regarding this conversions. So you have this representing the y component and this representing the z component of the unit vector. R basically we know is defined as follows. And so making these substitutions into the original expressions, we end up with F1 basically looking like this for outside the cylinder and looking like this inside the cylinder. But now these are written in Cartesian coordinates. All right, so we're going to rewrite F1, F2. Step 3 is to rewrite F1 and F2 with respect to the plane of symmetry, planar axis symmetry, which if in case it's cylindrical, or point of symmetry if it's spherical, and we translate back to its original location. And so basically, this is similar to the description that was given previously. This is a mirror image of what we had said earlier. The only difference now being that the point at which things pass through has been changed from the origin to a point which is displaced by minus a minus d over 2 units along the z-axis, the negative z-axis. Okay, so for the cylinder, basically, we end up having the original point. This is the point of the axis symmetry. This is the measurement point. And again, it's the difference between the two that we're needing to calculate. And then we basically make the substitution to the original expression for f. Z and y get replaced by z1 minus z0 and y1 minus y0. And since we're exterior to the cylinder in terms of the measurement point, this is the appropriate expression to use. This can be simplified and you'll get it to a form shown here. And so this is basically the total answer that we get. We go through the same process for the slab. For the slab, basically, we have the plane of symmetry, point on the plane of symmetry is 0, 0 minus a minus d over 2, but the observation point is exactly at the same location. And so when we take the difference between the two, we get 0, 0, 0. Well, this corresponds to basically computing the field at the center of the slab, and so we use the appropriate expression for F2, and that happens to be this one, where Z is now replaced by Z1 minus Z0, and this ends up being a value of 0. All right, so the next step basically is to compute the total field. So here's the field due to the cylinder as observed at the measurement point, which is sort of the midpoint of the slab. And this is the contribution of the slab, which was 0. If you add the two together, we end up with this result that's shown here. Anyways, that concludes Lecture 25D. Thank you for listening.